Morning, everybody, and welcome to Astronomy. Let me pull first of all the class in here because I want to share with you the resources for this class to make sure I have the same. Astronomy 100. Let me change the view to a student view. Okay, we're in good shape now. Oops, I did not change it to a student view. I need to reset the view because sometimes when I do things and then okay, so let me make sure I'm in student view again. Okay, again, welcome to Astronomy 100. Today is September 8th. Normally we meet on Monday, but because of the fact that Monday was an off day because of the holiday, so I thought we should meet on Wednesday, knowing that some of you already have prior commitment in terms of work and in terms of also other classes. As a matter of fact, I received some messages from you, some of you guys that you cannot attend today, but you know that if you cannot attend it live, you have to really watch it recorded later on, because there will be assignments based on this topic. This is probably by far one of the most important topics that we're going to learn in this class. So it's important that you guys do what either watch it live, and I know that there are a few of you in here, but those who are not in here, you really have to watch the whole thing and take notes of it, because this unit is of extreme importance, and I will exactly demonstrate why it is important. You will know exactly why this is important. Conceptually, first of all, the concept itself is very critical. Then the other thing also is because it entails a lot of implications in terms of our nowadays, basically, technology and civilization, because a lot of things what happened in the 1600s influence what happened in actually the later centuries until today. So that's why it's important. The other thing also why it's important is because they're going to be tested thoroughly on it. There will be an item discussion today, so it's a participation. There will be quiz on it, so that's going to be tested on it again in a different format. You will have homework assignment on it, so that's another way. And finally, it's going to be tested in exams. So it's important. Okay, so basically, if you don't think that it is important in terms of other parameters, which is, then at least in terms of testing grades, it's an important unit. And it's only one unit for 1 week, so it's really not bad. Now, before I get into it, let me talk a little bit about the message that you received from me yesterday, 7:30 in the morning. And then also about a message that you will receive around 1 p.m. today from me. Two things, okay? The message that you received yesterday, 7:30 in the morning, dealt with the meeting tomorrow at 9 a.m., okay? Some of you expressed concern about Stellarium in a sense that it was not working for them. They could not install it. And for apparently a good reason that I didn't know before existed. This is the first thing. You see, no matter how much I teach this class, every time I come in, I learn something new. And I really learned that the Chromebook does not allow the installation of the Stellarium software. I don't know, honestly. I think Chrome itself is a Linux version, is a Linux flavor. So I did not really test it. Probably I should test it with one of the other Linux distributions. There are one of the Linux basically installers. There were 3 of them. So maybe down the road I have to test it myself and see if it's going to work. But there is actually a solution to that, and the solution is the web version. So even if you cannot install it on your computer, which is a Windows or a Mac, where you have the installers in there, because of the fact, let's say, for example, it's a loaner computer, or a computer does not meet the minimum requirements and so on and so forth, okay? And if you cannot install it, then there is the web version, which is a solution for everything. Anybody can use the web version, because as long as you have access to the internet, you should be able to access the web version. However, the web version has an issue, okay? The keyboard shortcuts don't work on the web version. And that's the assignment I gave on week 2, was all of the instructions using the keyboard shortcuts. You can do away with the keyboard shortcuts and use the mouse instead. That is really what we need to do on tomorrow, is to make sure we complete the activity step by step, using both, okay? Here is how we can do it. As a matter of fact, I plan on opening it both on a website and also on my desktop version, and make sure both of them are working. Click here, click there. If it asks you to slow down the clock, there is a way of slowing it down. If it asks you to expedite the clock, there is a way of doing it both with a shortcut and also with the mouse. In other words, the purpose is to be familiar with the software to the point where we complete our assignments. Because down the road, there will be a project, and at least one project, if not more than one, where we really need to use Stellarium. So it's important that we need to be familiar with it. The purpose of the week 2 activity with the Stellarium was just to get us in that point where we are ready to use it. So that is where the meeting tomorrow is. So if you guys are 100% comfortable with Stellarium, have it fully installed on your computer, did the activity and don't have any problems, and think that you have it from top to bottom and you understand everything, then there is no really need for you to attend tomorrow's meeting at 9 o'clock, or even watch it later on in the recorded. You have complete freedom in here. There is no assignment, in other words, associated with tomorrow's meeting. So if you don't attend it, you're not gonna miss points. That's the point of it. But if you had a problem with installing it, or if doing the demo, for example, or even if you did not have a problem but feel that you would want to attend, then I recommend that you do attend either live or watch the recording later. So that is basically what that is. I did not send you the link to the meeting yesterday with a reason, because just before the meeting in the past, somebody goes into the email and try to find where the link is, and it's way buried down in the inbox because of message that pops up afterwards. So what happened in this case, on tomorrow, 8 o'clock sharp, you will receive a message with me with a link to the meeting. Okay, that way you will have it right in the top of your inbox if you decide to join us around 9 a.m. So you'll have the link there, you click on it and you're with us in the meeting. It is not going to be on Confer Zone. It's going to be a separate meeting, okay? So that is basically the message I sent yesterday, 7:30 in the morning. The message you will receive today at 1 o'clock from me, it's a survey actually, because I make a big fuss over teamwork, and it is important in my opinion, because not just because it helps us do homework and projects, but because it's actually a skill that we need to develop. It doesn't matter which field you're going to be working in, whether you're working with a fire department, in the medical field, it doesn't matter where you go. Teamwork skill, the skill itself is a valuable skill. You may be very good at what you do, but if you don't work well in teams, you will have difficulty. So that is one thing that we want to, I want to at least for you guys to have a sense of. The other thing also, even in science, as a matter of fact, if you look at any publication lately in science, it doesn't matter, astronomy or any field in science, you will see a bunch of names listed for the people who worked on the project. That is what we want to do. Yeah. So the purpose of the survey is to see if you already have a team working with you, that is good. If you don't have a team, I will try to pair you with other students to work in teams, because we have work that is needed down the road. So that is the survey that you're going to receive later on today. Hopefully you will have the time to fill it and respond to it, okay? And I will ask for your student ID, because I would want to match the ID with the, because sometimes what happened, a person fills out the form and decides, you know what, did I do it right or not? Or maybe I have a change in opinion, maybe I really, my teammate dropped, so I need to go back and refill it. So in this case, I will match the multiple responses to see. So I really need your student ID there in this survey. So that takes care of business. So let's talk about this week, which is a very important week. So I'm going to share with you a screen. This is where we are, week 4. I'm looking at it from the vantage point of a student, so that this is how it looks to you, okay? This is typical. Now you have been seeing this every week, that you have the previous week review. So I recommend strongly that you go through those videos and do those demos and basically make sure you're read all of these units, okay? you read all of these these 4 units. That is part of what you have done. There is an assignment that is from the previous weeks, and it's due this weekend, actually. So make sure you fulfill those. And then you have an assignment that is due the next week. And this only has a single unit that we're going to be talking about this week. Okay. As I believe, and I already expressed the idea that this is a very, very important unit. Okay. So I'm going to go through this content of this unit. So let's dive into it. Let me pull the topics, that the objectives for this unit, and let's talk about them. This is not, again, a replacement of what you're supposed to be doing, which is a reading of these units. Again, these are the 4 objectives for this unit. Okay. The first one is talking about this guy, Tycho Brahe, Kepler, and Galileo, these people. Okay. I really should probably squeeze in here Copernicus, because Copernicus is the one who steered the whole thing. Okay. We're going to talk about the ellipse and the properties of the ellipse when we talk about Kepler's laws. Okay. And I'm going to even interject the name of Newton in here. And that really puts the whole thing in focus and why this unit is extremely important. When we list the 3 laws, I'm going to pick up the book on page 95, and I'm going to do some sample calculations. What is expected from you to do in this unit? Okay, the type of calculations you will do. And then in talking about Galileo, I'm going to talk about this point in here and relate it to his observations. So this is basically the whole unit in here in a nutshell. Okay. So what's the deal with Tycho Brahe, Kepler, Galileo, and before them Copernicus? We are toward the 1600s, and before that, the 1500s and something, around to the end of the 16th century. The calendar was a mess, so Mr. Copernicus was asked to fix the calendar. Remember, at that time, and even today, today, if you go outside and look at the sun and track it, its path in the sun, you will see the sun rose in the east and it's going to set in the west. Like everybody else at night also rises in the east and sets in the west. As far as I'm concerned, I could be sleeping on the floor, basically looking at the sky, and I see everything revolves around me in what looks like a circular path. So that was the idea that was held for thousands of years, the geocentric model. Everything revolves around us because we are important, apparently. What makes us so special? We are it, as a matter of fact. And they go in circles. They believe the circle is the most perfect shape because the heavens are perfect. Earth is a mess. It has valleys and crevices, and it has mountains and hills and things like that. And that is because we humans are bad. Basically, we sinned. That's why Earth is as such. So that is the idea that floated for thousands of years. And Ptolemy built his model. One of the problems he ran into was the retrograde motion of Mars, and he insisted on the circles, going in circles, and so on and so forth, that we know about. Copernicus, when he tried to fix the calendar, he saw there is a flaw in the whole thing, and that is the Earth is not the center of everything. At least as far as the planets are concerned, the sun is. The sun is the center of the solar system, and we discussed this before. This is the heliocentric model versus the geocentric model. This is basically the whole point, the difference between them. I mean, for me, at least, and sometimes I think I'm smart if I go outside, there is, I think everything revolves around the Earth. It's easy for me to convince myself of the geocentric model than the heliocentric model. So that is the point in here why Copernicus' work is so critical, because it was a revolution. Okay, he did not abandon though the circular paths, and that was led him to an issue. So later on, Tycho Brahe, basically, who was a wealthy Danish person, and then he basically moved to He built actually an observatory in an island near Denmark. He monitored the skies and collected a lot of data. So that is really critical. So now we have valuable observations. He did not have a lot of tools. He did not have a telescope, but his observatory used some tools in there to measure the angles and basically the different positions at different times. And he collected a lot of valuable data, and that data was the basis later on for the work of Kepler, because he hired Kepler, but he was too protective of the data. As a matter of fact, Kepler did not have access to the data until Mr. Tycho Brahe passed away. Then in this case, Kepler looked at all of that data, and the first thing he came up with is the planets do not orbit the sun in circular paths. They orbit the sun in elliptical paths. That was one thing. What was a major deviation? Of course, the data does not lie. I mean, you're looking at the arc, and you follow the arc, and it's not arcing as an angle of where it goes on a circle. It's going more of an ellipse. Okay. So that was the first thing he noted. The second thing he noted is that I'm gonna let me switch cameras in here, because that's probably more convenient to describe his laws. Okay, so I'm gonna switch cameras. And I have this camera in here that gives me, let me go in full view mode. Let me remove, skip the screen share so that you guys see the whole thing. It's better with the whole camera in. So this is basically the conclusion of Mr. Kepler. This is the first law. And what an ellipse is, first of all, it's just two focal points, and it's the collection of points that are at the same distance from these 2 points. So if you're curious how I built this one, I took this string and I wrapped it around this. I made it loose in purpose. Okay, wrapped it around these 2 focal points. Now the string is non-stretching, as you can clearly see. It's a non-stretching string, basically, and I ran it through. Okay, until I constructed the ellipse. Okay, that's how you make an ellipse. Now, the point being in here for the ellipse is this length does not change, meaning this distance and this distance is the same no matter how far I am on the ellipse. If I am here, it's this distance. So this is really as opposed to the circle. The circle, if I take the center of the circle, it's all of the points that are at the same distance from the circle. Whereas the ellipse, as you can clearly see, is all of the points that are the same distance from 2 points called the focal points. Okay. So the sun sits in one of the focal points, and this is the other focal points where there is nothing in it. So if you ask me where the sun sits, it doesn't matter. Just pick any point. So that is his observation. The ellipse is characterized, as you can clearly see, by these 2 points, what are called the focal points. The plural focus, which is a foci or foci, those are the 2 different points. The sun sits in one of them. I took the yellow one to be the sun in here. So this is the first law of Kepler. All of the orbits are ellipticals, except this distance from here to here characterizes how flat the ellipse is, basically. We call this the eccentricity of the ellipse. If these 2 points come together and they fall on the center, for example, this will be the same distance for all of them. It becomes a circle, basically, instead of being an ellipse. So circle, if you wish, is a special case of an ellipse where the 2 focal points have no distance between them. They are the same point. Okay. This one is exaggerated. If you look at any planet, the 2 focal points are actually inside the sun. Okay. So this is exaggerated. I made them very far away, but the 2 focal points in the case of because the distance is very small. So the eccentricity is very small. So most of the path, they look very close from circles, and that's what got the confusion with Copernicus. Okay. Other than that, if you look at different objects, for example, if you could look at Mars, especially, Mars has a bigger eccentricity than Earth, for example, but not that big. But if you look at the path of Pluto, Pluto at sometimes goes inside the path of Neptune, and sometimes it's far away from Neptune. That is because its path is actually very, very eccentric compared to Pluto or a lot of other planets, compared to Neptune or other planets. Comets, though, they're notorious for high eccentricity. A comet, it's very far from the Earth, from the Sun, I'm sorry, which is the Earth. When it's very far, it's an icy object. When it gets closer, when it's about 5 astronomical units, it starts to warm up and develops a tail because of the vapor that is going to develop out of it. And then it's close by, and then it's going to go and starts to freeze again until it passes Jupiter, and it's completely frozen and comes back as a rock. A rock when it's far away, and it's basically a loose structure in here, and that's what the comets are. So comets have a very eccentric path, and they're the ones that have the most eccentric path that is known, actually, because of that. But the point in here is eccentricity, which is a property of the ellipse, is the measure of how far the two basically focal points are, relatively speaking, compared to how far these 2 points are. What are these 2 points? This is the closest point to the sun, which is called the perihelion, or a summer solstice on Earth. This is the aphelion, which is the furthest point from the sun. I'm taking this to be the sun, the furthest point to the sun. So this is the aphelion, or the winter solstice. These are the 2 equinoxes. This is where we change from winter to summer, or summer to winter, okay? So these are the 2, this one is summer to winter. This is September 21st, and this is March 21st, okay? The 2 equinoxes. So the Earth goes in this path, and so do all of the planets, by the way, okay? This distance from the aphelion to the perihelion is called the major axis. As you can clearly see, it's a big length, okay? Compared to this distance, which is called the minor axis. Half of this distance from the center of symmetry where the 2 meet to any point, either the aphelion or the perihelion, is called the semi-major axis. Usually in algebra, we use the lowercase a. This whole distance from here to here, we call it 2a. This distance only is called, half of that is a. This distance from here to here, we call it 2b. But half of that is the semi-minor axis, or b. This distance from the 2 focal points is called 2c. Half of that is basically the property that we talk about in terms of the eccentricity. So if we're going to do math, this is basically how the properties of the ellipse are. So the properties of the ellipse are the 2 focal points, the semi-major axis and the semi-minor axis, and the eccentricity, which is a measure of how far the 2 focal points are versus the semi-major axis or the major axis. So this is basically how the properties of and I know this is I listed as item number 2 in the objectives, but this is basically law number 1. All the planets, it doesn't matter what, they go in elliptical paths. Law number 2 is kind of a difference, okay? Look at it. If I take an imaginary line from the sun to the Earth, for example, or any planet for that matter, it doesn't matter, and wait for a period of time. It doesn't matter how much period. I took a month in here. Let's say, for example, in 1 month, the planet goes on this arc. So this is the area this line will sweep, because this line was here and it goes all the way here, okay? So this is the area this line will sweep in 1 month in this side of the sun. If I wait, if the Earth was on the other side of the sun and moving, if I wait 1 month, it's going to move just this arc distance. It's not going to move that big of an arc distance. It's going to move slower. So that this area swept by this line is just this much, okay? But this area and this area are equal. Why they are equal? Although the arc distance is less in here than in here, but the radius in here is less than this radius, okay? The area is proportional to the radius squared, okay? So, and the arc displacement. So what's going on in here? then in this case, it seems like the planets speed up because it covers this much Earth distance in 1 month and slows down when it's there. So this is how it goes. It's going to go slow, 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 and then picks up speed and then slows down. Then it becomes very slow in here, and then it's going to pick up speed and then slows down, and so on and so forth. So it goes like this. Okay, so that is basically what's going on. So the second law says the area swept by this imaginary line, this is not a real line, is at a constant rate. Meaning, if I wait 1 week, I will have one area. If I wait a week anywhere else, I will have the same area. Okay, so that's for law number 2. Law number 3 is a little bit different. If I take a planet, it doesn't matter, Earth or anything else. If I take Earth, for example, today is September 8th. Let's say, for example, September 8th, the Earth is in here, okay? If I go on the circle all the way and come back September 8th, 2022, I will be back in the same points. So that is 1 year. So we call this one a period. Obviously, for Venus, its orbit is different in here, where the sun occupies the focal point, the same focal points in here because it's the same sun. The planet in this case will have a shorter period of time because it's closer. As a matter of fact, it will take about 7 months to go once around the star. So once around the sun. So if we were here in Venus, and if we come back in here, Venus would have completed the cycle and it's probably here already. Okay. But for Venus cycle, it's less, it's about 7 months. For actually Mercury, which is very close, it's about 3 months. For Mars, it's almost 2 years, and so on and so forth. So this is the period P, expressed in years. This distance, as I was saying, is A, the semi-major axis. Well, the third law of Kepler basically says the following, that the square of the period in years is the same as the cube of the semi-major axis. So those are the 3 laws of Kepler, okay? These are the 3 laws of Kepler in all of their beauty, okay? All of these laws are based on observation. They're based on what you see, okay? Based on the observation of Tycho Brahe. The third law took him a little bit of time to come up with it, but he did come up with it at the end. His work spent a lot of time, basically. He spent almost 40 years altogether from the time he started with Tycho Brahe until he finished all of his work, basically. And because of the wealth of data. Obviously, at that point, everything looks kind of, some people still have, there were still skeptics at that point, okay? About even the fact that the sun is the center of the solar system and not the Earth is. The Earth is the center of the system. We are it, okay? What are you talking about? I can go outside and look at it, okay? Until Mr. Galileo, and this is part of the first objective, by the way, took a toy in the early 1600s, 1609. He took a toy at that time kids used to play with, which was a telescope. And telescope is basically made up of lenses. And a lens, what it does is it takes rays from infinity, from very far away, and focuses it. If you have played with a lens, that's what you do. Take rays and basically focus until you make fire, basically, out of it, okay? So, he turned that telescope to 2 objects. First of all, to Jupiter. And he noted the first night that there are 3 objects revolving around Jupiter. The second night, he noticed the 4th one. The first night, he saw Europa, and he saw Ganymede and Callisto. Those are the 3 moons of Jupiter. The next night, actually, he saw Io. Io is so close from Jupiter that it takes only 42 hours to go once around Jupiter. It's very fast. So if you don't see it tonight, just wait until tomorrow and you're going to see it, basically, okay? Whereas the other 2 or 3 moons, you'll have to wait a little longer because they're far away from the moon. Now, the point that I'm trying to make in here, these 4 moons are known now as the Galilean system or the Galilean moons, okay? Because he's the one who discovered them. What Mr. Galileo has done actually is that, look, you guys are telling me that everything must revolve around the Earth. Here is an example. You have Jupiter and 4 objects revolve around the Jupiter. So this idea that the Earth is center of everything and everything must revolve around us because we are a big deal and so on and so forth is not true. Because here is an example of Jupiter where you have 4 moons revolving around it. So that was a big confirmation of the work of Copernicus first and Galileo and Kepler second. Okay, because of the fact that we are not in a geocentric model anymore. We have actually more sound system for the planets is a heliocentric model. So that is important. The other thing also, he turned it to the moon. And he noted that those dark areas in the moon, they are nothing but shadows cast from the sun on the hills on the moon. So the idea that everything has to be perfect in circular path in the heaven, and they are not so perfect here on earth because man sinned and so on and so forth, is not true. Because here is a celestial object, which is the moon, which has hills and valleys and crevices, just like the earth does. Where is the person who sinned on the moon for this to happen? So that is why his work is so critical. In addition to the fact that he worked on the acceleration, he worked on the motion, and he laid the foundation first law of Newton, and he actually calculated the values of the acceleration. He calculated it, he measured it actually with his, he did not have access to a watch. So what he did, he used his the pulse on his from his hand to measure the G, which is a very important value. Because later on, Mr. Newton came up and took all of the work of Galileo and built on it 3 more new laws. Basically, he came up with the laws of mechanics, which have nothing to do with the laws of Kepler, by the way. The laws of mechanics that basically state that an object that is at rest will remain at rest if it's under no net forces, or continue moving in constant speed if it was moving to begin within the same direction. That's law number 1. That is the work of Galileo, actually. Law number 2, it says basically that an object under net forces will accelerate in such a way the acceleration is the ratio of the force over the mass or the inertia. And the third law is basically if 2 objects interact, they do so in such a way, if one exerts a force on the other one exerts a force that is equal in magnitude but opposite in direction. That was all good and dandy, but he was a student at that time. He was not a faculty or professor or anything. He did not even have his degree. So he was a student when he came up with this law, with this laws in London at that time, just around the time when Kepler actually, toward the end of the life of Kepler, something hit London. And it's similar to the condition we're in right now. The pandemic there in London, namely the plague. Everybody in school, everybody in colleges and universities was sent home, just like what happened to us now. The only problem, the only difference is they did not have Zoom at that time. Remember, we're talking about 1650s. Okay? So they could not continue studying online. So they had to basically abandon all schools at that time. That's the plague. It took about 2.5 years or 3 for people to basically, for the disease to basically be controlled. We are almost on the same timeline too, right now. Okay? It seems like there are parallels in there. So what Mr. Kepler was, what Mr. Newton was asked to do, he was handed the 3 laws of Kepler, and he was told, here is what Mr. Kepler has come up with. These 3 laws that I was describing to you guys earlier. Can you explain them in light of what you have told us in terms of your laws? Remember, he was still a student. So what he did then, he came up with the universal law of gravity based on the comparison of an apple falling on the earth versus the moon rotating around the earth. And he made the hypothesis that this is the same law that governs the motion of all of the planets on this in the solar system. Not only that, all the objects in the universe governed by these laws. He was able to explain the 3 laws of Kepler. The solution to his equations for the motion yields the elliptical paths. And the ellipse is just a special case of the so-called conic shapes. If you take a cone and you cut it parallel to the base, you know, ice cream cone, and you cut it parallel to the base, it's going to produce a circle. So the circle is a special conic shape. If you cut it at an oblique angle, you're going to get an ellipse. If you cut it at a special angle where one of the places that you run through is the top of the cone, that is actually going to produce either a parabola or a hyperbola, depending on where you're going to end up at the end. If you're going to end up back in the base, that's a parabola. If not, you're going to end up in a hyperbola. So all of this 4 conic shapes are a solution to the equations of the universal gravitational law, including the ellipses, which are actually included in here. Furthermore, there was something that was not clearly stated in the work of Mr. Kepler that was evident from the solutions of Newton, is that all of these planets must be on the same plane. I mean, if you look at them now, you'll see them slightly on and up. I mean, off, slightly off on the plane. It's called the ecliptic plane. All of these planets, if you monitor them in the sky, they go in the same line. Why? Because of the conservation of the angular momentum. That's actually a solution to his equations. Conservation of the angular momentum has two things. It has direction and it has magnitude. The direction forces them to be on the same plane. The magnitude is the second law of Kepler. It's actually the area of the angular momentum is the magnitude. So that area is constantly changing with a constant rate. Again, beautifully stated. The third one required a little bit more work, and that has to do with the conservation of energy, and that led to p squared equal to a cubed. So he was able to explain Kepler's laws. Was that enough for him? No. If anybody comes to you and tells you, look, what you have seen, I can explain it to you. The reason why the plane is flying, he tells you, is because, fill the blank. Doesn't matter what you're going to tell me, okay? The reason why the plane is flying is probably because of an angel or because of something that is pushing it, or I don't know, okay? Or somebody is dragging it, you don't see him or something, okay? But if that explanation, all it does is explain things, it's useless. And that's the same thing the case also with Mr. Newton's work. So Mr. Newton, and the reason why I'm emphasizing this is because what happened then with Kepler and all of that time really is where we are today, because that's how the scientific method works. If somebody in science comes to you and explain things, and if all he does is explain things, that is not good enough. You need to go a step beyond. So immediately, first of all, he was able to find the constant. Why p squared, the square of the period, is proportional to the cube of the semi-major axis. It's because of the mass of the sun. Because if I take these numbers, apply them to the Jupiter, it's actually different constant, and that different constant is actually the mass of Jupiter. So now it became a way for me to measure masses of all kinds of objects. You see, from now on, when somebody comes to tell you that the mass of the supermassive black hole in the center of the galaxy is 4 million times the mass of the sun, you wonder, did anybody go and weigh that thing? All we did was observe the stars as they go around the center of the galaxy and how fast they go. Based on that, we find the constant based on the theory of Newton, how much that black hole is, how big the black hole is. Somebody comes and tell you, hey, Betelgeuse, which is a big star, has this much mass. Did anybody go and weigh Betelgeuse? No. Did anybody weigh our sun? No. Okay. So you can't really tell me that. So it's based on these things that Mr. Newton was able to push further the work of Kepler and was able to find that that constant is actually the measure of that mass. That's not just there where it ends there. Mr. Newton's work, which was a theory to explain what Mr. Kepler has done, based on the work of Galileo and everybody else also, he was able to do something else, and that is to, not him, Halley actually, looked at a comet that came visiting, and he said, okay, if I believe the work of Mr. Newton explaining the work of Mr. Kepler, this comet will come back 76 years from today. On such and such date, he predicted the day when it's going to come back. Within a day or two, 76 years later, it shows up again. That's amazing, okay? Somebody can make a prediction for that long, 76 years. With that much accuracy, it's outstanding. That's what the Newton's work did. Furthermore, when Uranus was discovered, and it was discovered with telescopes by Herschel, and actually other observers also, there was a problem with its motion. It's supposed to go on an ellipse like everybody else, but at some point it was wobbling. Two mathematicians, independently and knowingly of each other, one in Britain and one in France, took that wobble and thought maybe there is another planet and calculated the position of that planet and how big the planet is. It's going to be a big planet and it's going to be in this position. So the first one, the British one, sent his work to the British Royal Society, Astronomical Society, and they did not really follow up on his work soon. But the French one sent it independently and knowingly of the other one to the German, basically similar, where they have an observatory in there. Sure enough, they turned their telescopes into the position where the calculated values were for that planet, and that's how Neptune was discovered, based on math. Based on math and pure math only, okay? Based on the work of Newton. You see now, you go a step further. See, that's how the scientific method works. It's not just explaining things, but can you make predictions with those things? New levels of knowledge. Then that theory becomes more and more acceptable and becomes true. There was a problem though, a nagging issue big time at that time. The problem was Mercury, actually. Mercury's path was not as good as it should be. Mercury's path, as a matter of fact, was everybody is on the ecliptic. It was really coming on and off of the ecliptic, okay? Number one, in that precession, as it goes around the sun, was an issue. And they tried to correct it. Maybe Venus has an impact on Mercury. Maybe we include the Venus as a gravitational pull. Well, does not do that much. Maybe we include the Earth. Maybe Jupiter. Jupiter is a big player in the solar system. See how all of these corrections did not really do well for Mercury until the beginning of the 1900s, which is the 20th century, when Mr. Einstein says, you know what, Newton, you did good, but not good enough. I have a better explanation for you. That explanation of Mr. Einstein, which is the general theory of relativity, explained, of course, what Kepler has done, explained what Newton has done, explained everything else, and it had to go a step beyond, which was to explain Mercury. Is this good enough? No. If all of that Mr. Einstein's theory was to explain what happened with Mercury, then again, it's not good enough. You have to make predictions. One of the things he predicted, for example, is gravitational lensing, which we're going to talk about it. There was a solar eclipse in 1919, which was almost 10 years later after he came up with this theory, that prediction actually was confirmed in the solar eclipse. So there were actually other predictions that Mr. Einstein came up with. You see how the scientific progress happened from that time, from this unit 12, which is the 1600s, and actually before, slightly before that, all the way to where we are right now, where we stand in terms of science and technology. Actually, all of these things came in consequence of those things. So it's a very important unit in terms of its historical context, in terms of where we stand as civilization, in terms of the scientific thought, in terms of scientific method, and in terms of how science progresses in general. That's really why it's important stuff that we know that. Okay. Let me share with you the screen to talk more about the objectives and see where we stand on them. So did I share? I did not share. Okay, now I think I shared. Okay, so we talked extensively about this two things. We talked about this last one in here, the telescope and things like that. What we didn't talk about is the three laws. We talked about the three laws, but what we didn't do is carry out calculations using each and every one of them. So I'm going to stop sharing that screen, and I'm going to go and share with you another screen. And let me pull another line in here. And let me pick up another color in here. And let me share the prompt of the day, which is important. Okay, so what are we supposed to do today? You're asking? Well, we're supposed to list the three laws of Kepler. So this is what we're supposed to do today in the discussion item, okay? Because of their extreme importance. So the first law basically says the following. Planets orbit the sun in elliptical paths where the sun sits in one focal point. You're asking me which point that is, it doesn't matter. One of them, pick and choose, okay? So that is law number one. Law number two, the imaginary line. So let me rewrite it. The imaginary line. So I'm trying to say in here, it's not a real line, it's just basically a mathematical line. The imaginary line joining a planet to the sun, it doesn't matter which planet that is, sweeps equal areas in equal amounts of time. Okay. Law number three, basically it says that the square of the period measured in, I'm going to write this in capitals because it's important to note this. So it's measured in years, not in seconds, because typically we measure time in seconds. Since period is a time, we're tempted to put it in seconds. If you put it in seconds, there is a constant number that you have to put. So it's not the same thing in here. So it's measured in years, is equal to the cube of the semi-major axis. That too has a special unit in it, measured in astronomical units, AU. Okay, so that too is important, okay? Normally you measure distances in meters in the metric system. If you measure the distance in meters, and if you measure the period in seconds, that constant has a different value in it. So they're still proportional. The ratio is the same for different planets. So in other words, written this way, I can write p squared is equal to a cubed. If you choose different units of system, you can say this planet one, if I take this ratio of its period over its cube, is the same thing as any other planet. It doesn't matter what that is, which is a constant, and that constant is what Mr. Newton has found. Okay. Now, I put it in my own words. You can choose your own words. You can look at the book. You can Google it if you like, but these are the 3 laws of Kepler that you're supposed to put in the discussion item today. So let's tag into the second part of the objective, which is to do calculations. So for calculations, I'm going to open page 95 from the book. And I'm going to pick up 2 planets from that table. And the planets I chose are going to be Venus and Jupiter. Okay? So Venus and Jupiter. From the book, Venus has a semi-major axis, namely A, equals to 0.723 astronomical units. That means it's about 3/4 of the way from the sun than the Earth is. The period P for Venus, that means how many months it takes, how many years it takes to go once around Venus. It takes slightly more than a year, than half a year, slightly more than 6 months, but slightly less than 2/3 of the year, which is 8 months. So it technically takes about 7 months, really. So that's the period. So what I'm supposing here is to check is it true that p squared is equal to a cubed? I don't know. Let's check that. So what I need to do is take this number and square it. P squared, that means 0.615 times 0.615. If you have a calculator that does the power, then you use the power too, okay? So I should have a calculator in here ready. So I'm going to stop sharing And I'm going to share the calculator and find what this number is. And this number is 0.615, 0.615, not 615, 0.615 times 0.615. So that is 0.378, and then some change. The reason why I don't retain the change is because I only have three significant figures in here. I have the 6 and the 1 and the 5 that are significant. So I cannot retain really more than 3 because I started with 3. So in this case, I'm going to only retain the 0, the 3, the 7, and 8. Before I do that, I'm going to ask, is the 2, 5, this 2, is it 5 or more than 5? Obviously, it's less than 5. So if it's less than 5, so I'm going to round down. So I'm going to ignore that number, put it to 0, basically anything after that. So the correct answer in here is 0.378. So if I plug in the number in here, in my calculator, oops, am I sharing the calculator still or the notes?
The notes.
Okay, very good. So according to this calculator, this number is 0.378, okay? So that is this number. I need to check a cubed. Now, a cubed is 0.723 times 0.723 times 0.723. And the question is it the same number? If it is, then it checks, okay? So let's do that. So let's kind of stop sharing the screen. I'm gonna share the calculator again. And the calculator told me to check 0.723 times 0. I could do the power, but it's okay. We can do it this way too, times 0.723. And again, the calculator is giving me a lot of things in here. All I need is to retain 3 of them, but I have to be careful. I ask the question, is this digit 5 or more than 5? And the answer, yes, it is 5 or more than 5. So I have to round up. I cannot round down like the first one. So the 9 becomes a 10. Any number that was more than 5 or 5 has to be rounded to a 10. So the 10, I have to carry 1 in here, and this 7 becomes an 8. So the answer in here is 0.378 when I retain just the sig figs. So if I share again the notes, that is actually 0.378. So indeed, the two numbers are the same. So that means, yes, it checks. Okay, so Venus checks. Let me look at the same tables in here and pick up Jupiter. So for Jupiter, I have the semi-major axis A is equal to 5.2 astronomical units, and the period is equal to, so it's 5 times further from the sun than the Earth is. That's what that means, slightly more than 5 actually. And it takes 11.86 years to go around the sun. So if you are 24 years old, you're actually 2 years as far as Jupiter is concerned, because Jupiter did it only twice going around the sun while you were born, from the time you were born. Okay, if you are less, then you are less than 2 years old. Okay, so you're still barely a toddler when it comes to Jupiter. It's different. So let's do the same thing. Now, is it true that p squared is the same thing as a cubed? Let's see here how accurate that is. So p squared is the same thing as 11.86 times 11.86. And this is going to give me a number. So I need to check it with a cubed, which is going to be 5.20 times 5.20 times 5.20. This is going to give me an answer. This is 3 significant figures. It's the 5 and the 2 and the 0. So I need to retain only 3 significant figures in here. The same thing in here, although I have 4 significant figures and 4 significant figures. So technically, I'm tempted to keep 4 significant figures, and that's true. But if I'm going to compare it with this one, I needed to really retain also out of it 3 significant figures. So at the end of the day, that is what it boils down to. So I'm going to go and share with you the calculator and see what this calculator is going to give me for both of these numbers. So it's telling me, first of all, the period 11.86 times 11.86. And although I have 4 significant figures, so technically I can stop at the 6. So it's 140.6. But I have to ask a question, is this number 5 or more than 5? And the answer, yes, it is. So I'm going to round up. So I'm going to add 1 to this number. So it's 140.1. 0.7, I'm sorry. 140.7. But I need to compare it with the other number, which is 5.20 times 5.20 times 5.20. And that has only 3 sig figs. So I cannot retain the 6 in here. I have to promote it because it's more than 5 to 1. So it's 141. So this one is 141. And this one also needs to be promoted up to 141. Both of them are going to be 141. So I'm going to share the screen now of my notes. And this is also 141. Although I have 4 significant figures, but I retain 3 because I want to compare these two. And you have to compare apples to apples. So this is a, and when it comes to significant figures, you're as strong as your weakest link. Because you have 3 significant figures in here and you have 4, you only go by the smaller one, which is 3 in this case. And both numbers are the same up to this degree of accuracy. So I can say safely that also this checks. This is the type of calculations that we're expected to do. Okay. Although there is other kinds of calculations that we might do down the road. And I did it in purpose this way so that you guys can see that it can be done without the need of a calculator. I mean, without the need of a fancy calculator. A simple calculator can do that for us. And that's basically in a nutshell how this thing is. So I hope that I have covered everything in terms of the concept that needs to be covered in here. Again, please watch the survey that you're going to be receiving today. For those who are watching this one recorded, you should have received it by now because the recording most likely is going to be available after the message that was sent. So the message is going to arrive today, September 8th at 1 p.m. So if you are watching this one recorded later because you couldn't watch it today or tomorrow and now it's Friday or Saturday and you're watching this one, you need to refer back to September 8th, which is today at 1 p.m., the message that you have received concerning the teamwork. And I hope to have replies done before actually when we meet next time, which is Monday. And where hopefully you already have a team working. If not, then I will have I will suggest for you some members. Hopefully you can work together. Sounds good? So I'm going to stop the recording now.